In this video, I want to talk about enthalpy. It's an idea easy enough that we could present it to 7th graders, but I'm going to make it both easy and hard. I mean, why not take something simple and tangle it up beyond all recognition? That is what thermodynamics does best. Enthalpy, H, is defined as a state function equal to the internal energy of the system plus the product of pressure and volume. In other words, H equals U plus PV. That is, it is the capacity to release heat plus the capacity to do work. Enthalpy depends on the size of a system, so it's extensive, but it's mostly used and tabulated per kilogram or per mole, and thus expressed in an intensive manner. It typically comes in joules, but it's often tabulated as joules per mole or joules per kilogram, extensive versus intensive. If you're an American in the heat or air conditioning industry or only have access to old textbooks, then you may also see it as expressed as BTU per pound rather than joules per mole or joules per kilogram. The above definition didn't just pop into someone's head in order to aggravate college freshmen. Rather, it was invented as a convenient way to express heat at constant pressure. From the first law, we can write du is equal to dq plus dw. That is, internal energy is equal to change in heat plus the change in work. What's more, we can take the change in internal energy and express it as a heat minus PDV because we're only going to consider pressure volume work. Next, I'm going to add the derivative of pressure volume to both sides. So here I have internal energy from right there. Internal energy plus dPV is equal to, I'm bringing down the change in heat, I'm bringing down the work term, and I'm adding again the dPV term. Then I will expand the derivative, but only on the right-hand side. So I take the dPV term right here and make it PDV plus VDP. Then I notice that this minus PDV term, which was brought down here, along with the expansion PDV term, are both plus and minus, and those get canceled out. Next, I can factor the term on the left-hand side. du plus dPV is going to be the same as the derivative of u plus PV. Collect the terms on the right, and then change to my definition, which is H is U plus PV. So then I have that the change in enthalpy, H, is equal to the change in heat plus volume times the change in pressure. And finally, if the pressure is constant, we'll have that the change in enthalpy is equal to the change in heat because the work term, VDP, at constant pressure will simply disappear. It is important to note that the definition does not require constant pressure. Our definition is enthalpy is equal to internal energy plus pressure volume. For chemical reactions, the PV term is sometimes said to be the work needed to shove the atmosphere out of the way and make room for a substance that's coming into existence. Or, if the volume is constant, as in the change in enthalpy is the change in heat plus the volume times the change in pressure, then enthalpy is the heat content plus the energy gained as a consequence of not being allowed to expand. This is all nice, but how can it help us to work problems? Usually at this point, we throw up an equation out of the blue that says something like delta H, remember that's the change in enthalpy, is equal to mass times the heat capacity times the change in temperature. Well, I'm going to do just a little bit of hand waving and try to show where this comes from. Talk about out of the blue. In the expression that I've put on the board here, we have a change in enthalpy is equal to the partial of enthalpy with respect to the partial of temperature at constant pressure times the change in temperature plus the partial of enthalpy over the partial of pressure at constant temperature times the change in pressure. Now, partial derivatives are pretty much definitions. Here we know that any thermodynamic state is fixed by two state variables, in this case temperature and pressure. Therefore, we say that the change in enthalpy is defined by the partial derivative of enthalpy with respect to temperature and the partial derivative of enthalpy with respect to pressure. For our purposes, it's just a definition. If we choose constant pressure, we know that the change in enthalpy has got to be equal to the change in heat. What's more, we can bring at constant pressure, we can ignore this right-hand term, bring down these two terms, and we know that enthalpy will be the partial of enthalpy with respect to the partial of temperature with respect to the change in temperature. Now we want to bring in the definitions of heat capacity. This is really an empirical observation over many decades. We see that the heat capacity, the constant heat capacity at constant pressure in this case, is the change in heat with respect to the change in temperature. What we're seeing is that there is a constant which, when multiplied times the change in temperature, is equal to the energy or the heat that has been put into or taken out of a system. And it's the same for volume if you're at constant volume. So if dH is equal to dQ, and dQ is equal to Cp dt, as from this expression right here, then we can come up with this complete equality. And furthermore, we can bring in this dH is equal to dH dt and show that, of course, that also has to be equal to Cp. This has been done with the intensive or molar definitions for enthalpy and heat capacity. In the more common problem situation, you'd use the intensive form, which is the form that we originally introduced at the top of the page, which has mass term, which could be either mass or moles, depending on the units of the Cp term that's used. So let's do a problem with this. Suppose we have a pure aluminum block with a mass of 20 grams at a temperature of 700 K, and we want to cool it to 298 K, or room temperature. We're going to be given a Cp value of 27 joules per mole K. So how much heat is lost? Well, the delta H is going to be the mass. That's going to be 20 grams divided by the molecular weight in grams per mole. So we'll have a mole term here. The next thing is we'll have the heat capacity at 27 joules per mole K, and then multiply that times the temperature. In this case, I have got the temperature T1 and T2 turned around backwards. This should have been 298 K minus 700 K to get the difference. And the only reason for that would have been that T1 is 700 K, but this should have been T2 minus T1, so that the answer actually comes out to be negative 8045 joules. Why is it negative? Because heat is being lost by the aluminum block. Think of it as a reaction. Any reaction that loses heat is going to have a negative delta H. Now suppose we add the complication that the heat capacity at temperature is not 27 joules per mole K, but rather is different at every different temperature. So Cp is dependent on temperature. Cp will have a different value at every temperature from 298 degrees all the way up to 700 degrees. So then our delta H is going to be the integral of the infinitesimal dH. Mass is going to be a constant, so it'll come outside the integral, but we're basically going to form the definite integral of Cpt dt for the entire range of interest. And that is going to make a whole different problem out of it. The first thing we need to do is to find an equation that we can both integrate and also mathematically fit to some data. So here's some data that I was able to find on the web for the aluminum, and it goes from 298 degrees K all the way up to 933 degrees K, and gives a range of heat capacities throughout there. And so I was able to, using some CAS software, you could either use GeoGebra, which is what I used here, or you might be able to use Excel to do the same thing. But I was able to both plot the data points and then turn around and fit a polynomial through them. And the reason I chose a polynomial is that it fits pretty well and it's very easy to integrate. So after doing the integration, or should I say doing the fit, the coefficients of the polynomial are a, b, c, and d, as shown here. And then the definite integral of this fitted equation is not that hard to do, and it's mass over molecular weight, and then this is the normal integral of a polynomial. And when I evaluate this from 700 to 298 degrees, then the new delta H is 7990.6. I've actually shown it as positive, but of course we know that it's negative. So the two answers for the first answer to this problem was 8,045 joules. This new answer is 7990 joules. They're very similar because the CP previously chosen was about halfway between the two temperatures, and as you can see, the curve is somewhat linear. Had it been otherwise, the answers might have been very different. So I've introduced the idea of enthalpy and shown one rather trivial use of it, and shown that we don't have to assume CP to be a constant. In the next video, I'll show how to derive the enthalpy potential using a Legendre transform. Thank you. I hope you've learned something.